Hey everybody, in this video we're going to be talking about what are called eigenvectors and also eigenvalues. So where this comes up, we're interested in equations such as a times x equals something like 2x or maybe negative 4x, where a is a matrix, and then where special vectors x are transformed by multiplying by a. So transformed by a into scalar multiples of themselves. So basically we times x by a and we get something that's just a multiple of x. So that's what we're interested in, and here's our definitions. So A is going to be an n by n matrix, and then we have that a non-zero vector, x, is what's called an eigenvector. And you can call it an eigenvector if A times x equals lambda x, where lambda is a scalar. So if you can multiply x by some multiple, some value, some scalar, and it's the same result as if you times it by the matrix A, we call that an eigenvector. Now this number, this scalar, lambda, we call that an eigenvalue. Okay, so lambda is an eigenvalue of A if there is a non-trivial solution for x if you solve this equation, ax equals lambda x. And then x is called an eigenvector corresponding to that eigenvalue, lambda. All right, so here's our first example. We have our matrix A, it's a 2 by 2. And then we have two vectors, u and v. So first we want to say, is u an eigenvector of A? So in other words, by definition, that just means if I times u by A, is it a multiple of u? Okay, so let's work this out. So A times u, here's A, here's u, and we just do our multiplication for our matrix. Remember, row 1 times column 1 is in this first spot here. And then we end up with negative 24 and then 20. And so now we want to ask, is this a multiple of the original vector u? So is this some lambda times 6, negative 5? And so we have our first row gives us negative 24 equals 6 lambda. And solving, we get lambda is negative 4. And then we try to solve the second row, and we get 20 equals negative 5 lambda. And we get the same lambda value. So that means that there is this eigenvalue, negative 4, and so u is an eigenvector of A, since A times u is the same thing as just negative 4 times u. Okay, let's see the same process, but now for vector v. Is v an eigenvector of A? Okay, so we know that that's just asking us, if I times A by v, or v times A, is it a multiple of v? Okay, so same process. We're going to times our matrix A times our vector v. We end up getting negative 9, 11. We want to know, is that a multiple of the original vector v? And so if we set up our two rows for our equations, negative 9 equals lambda times 3 gives us a lambda value of negative 3. But from the second row, we get 11 equals lambda times negative 2, which gives us a different lambda value. So there's not one scalar that would take us from this vector v to this result, which was A times v. So then we would say, therefore, no, v is not an eigenvector of A, since it wasn't, v was not a multiple, A times v is not a multiple of v. Okay, let's do another part to this question. Let's actually just show that 7 is an eigenvalue of A. So far we were trying to figure out if these vectors were eigenvectors, meaning were they multiples of themselves if we times them by A. Now I'm claiming that 7, the number, is an eigenvalue. So that's our lambda. If it is, find the corresponding eigenvectors. So that's just the same as saying, can we show that A times x is the same as 7 times x? All right, so first of all, notice we don't know what x is. And that's actually part of the question. So first we have to figure out, is 7 even an eigenvalue? And if it is, then we're looking for x. Previously in parts A and B, we were given the vectors. So right now we don't know the vector. All we know is that 7 is possibly an eigenvalue. So if you just subtract 7x, we have ax minus 7x equals 0. And then what we end up with here, if we want to change this into a matrix or matrix form, we're going to write this as 7 times the identity matrix. So if we just factor out x, notice what we get. A minus, it would be 7 times x, but we're writing this in matrix form. So 7 is the same as 7 times the identity, which here's our 2 by 2 identity. And we are choosing a 2 by 2 because A was size 2 by 2. All right, so now we want to write this as our matrix, or as a matrix. And so A minus 7i, here's A. Here's 7 times the identity matrix. And so A minus 7i is really just this 2 by 2 with these entries. Okay? And so now what we want to do is just figure out, is there going to be a solution to this? And notice that these columns are actually linearly dependent because they're scalar multiples of each other. If I times one column by -1, I'm actually going to get the other column. And from things we've learned in the past, that means that we have non-trivial solutions. Because previously we learned that if the columns are independent, there was only the trivial solution. So if we kind of just state that backwards, if the columns are dependent, linearly dependent, then there's non-trivial solutions. So what that tells us is that yes, 7 is actually an eigenvalue. There's non-trivial solutions to this equation. So next, we want to solve this equation. We just concluded, yes, 7 is an eigenvalue because there are solutions, or because, yes, there's non-trivial solutions to this equation. Now, let's find x. Okay, so we want to determine the eigenvectors x that satisfy this equation. And so we've done this in the past. We just set up an augmented matrix. Okay, and then we row reduce it. And notice what we get. We get a row of all zeros. So we do have free variables here. So from our first row, we know that we can rewrite it as x1 equals x2. And then from the second row, we can say that x2 is our free variable. And so in general, our solution for x is of the form x2 times the vector 1, 1. So any vector with this form, as long as x2 is not 0, would be considered an eigenvector, and specifically corresponding to that eigenvalue that we started with of 7. All right, so quick note, row reduction can be used to find eigenvectors, but not eigenvalues. Okay, so let's generalize what we've talked about. So lambda is an eigenvalue of an n by n matrix if and only if this equation has non-trivial solutions, a non-trivial solution. So this is exactly our example we just did where this was a 7. Okay, so if you're asked to figure out if some lambda value is an eigenvalue of a matrix, then you're going to set up this equation and just plug in your lambda value right here, whatever you're given. And so now just some ways to talk about it. The set of all solutions to this equation is actually equal to the null space of the matrix that we just worked with. In our case, it was A minus 7i. So this, as a matrix, the null space of that is the same as the set of all solutions to this equation by definition of null space, but it's also a subspace of Rn. But what I want you to know is the new term. This is called an eigenspace. So the set of all solutions to this equation is called the eigenspace of our matrix corresponding to that eigenvalue. And so the eigenspace consists of the 0 vector and all the eigenvectors corresponding to lambda. All right, so from our previous example, the eigenspace of A corresponding to our lambda value of 7 is just consisting of all the multiples of 1, 1. So where x1, basically what we had x2 times the vector 1, 1. So all the multiples of this. All right, so let's try this other example here. We have this matrix that's a 3 by 3. So an eigenvalue of this matrix is 2. So notice we're given an eigenvalue. What we want to do is we want to find a basis for the corresponding eigenspace. So the eigenspace, it's a subspace. Okay, and remember we've talked about a basis in the past. So basically, think of it like a foundation that could form the whole space by just doing multiples of what's in the basis. Okay, so we're looking for like the foundation vectors that would allow us to eventually form the whole space. In our case, it's this eigenspace for this matrix. All right, so what we are going to do is we're going to start with A minus lambda I. In our case, lambda was given as 2. So A minus 2i, and we set that up. Here's A. Here's 2i. It's just 2 times our identity matrix of the same size as A, so notice it's a 3 by 3, just do our subtraction, and we get this result right here. So this is the matrix A minus 2I. All right, and so then when we do that, next we row reduce our augmented matrix for this equation that we want to solve. Okay, so now we're just going to basically add another row, or column, excuse me, with 0, 0, 0 in it. Okay, so we set up our augmented matrix, because what we're trying to do is we're trying to get to x here. Okay, so we set this up, and hopefully you could tell, pretty straightforward. We can subtract the rows 2 and 3, and we're going to get all zeros there. All right, so at this point, it's clear that 2 is indeed an eigenvalue of A, and that's because we had some free variables for this equation when we solved it using our augmented matrix. And so in general, here's our solution. From the first row, we had that 2x1 minus 1x2 plus 6x3 equals 0. So we can rewrite that. Remember, you always want to rewrite that in terms of your free variables. Because x2 and x3 are free, we just say that x1 equals something in terms of x2 and x3. In our case, it equals 1/2 x2 minus 3x3. All right, so here we have our vector equation here. And so notice x2 and x3 are free, so they equal themselves, but x1 is written in terms of x2 and x3. And so what we can do is we've done this in the past, but basically think of it like factoring out the free variables. So if we factor out x2, notice what we get. In row 1, we had a 1/2. In row 2, we had just one x2, and then in row 3, we had just no x2s. Same thing for x3. Think of it as like factoring it out. And so a basis for our eigenspace is just the basis, the set containing these two vectors, the vector 1/2, 1, 0, and the vector -3, 0, 1. And so what this is a two-dimensional subspace of R3. And so basically, like we've talked about in the past, as with a basis, all the multiples of this would form our space. In our case, it's called an eigenspace, but in the past, we would just call it a subspace. All right, the last thing to tell you about is just a couple of theorems. So the eigenvalues of a triangular matrix are the entries on its main diagonal. So that's really nice. If you have your matrix in triangular form, then really quickly you can just tell what the eigenvalues are, just the diagonals. So in this case, it's 3, 0, and 2. In this one, you don't need to write anything repeated twice. So it's 4, 1, and 4. But don't write 4 twice. But notice this is still a triangular matrix. Normally we tend to rewrite matrices with the zeros in the bottom left corner, but this is still considered a triangular matrix, even though the zeros are in the top right corner. And so quick note here, 0 is an eigenvalue if and only if A is not invertible. So notice in this first example, 0 was an eigenvalue because it was one of the diagonals, and so this matrix would not have an inverse. It wouldn't be invertible. And the last thing to mention, this last theorem, if v1, v2, and so on are all eigenvectors that correspond to distinct eigenvalues, lambda 1, lambda 2, and so on, of an n by n matrix, then the set of those vectors is linearly independent. Okay, so that's our introduction to eigenvalues and eigenvectors, and that's it for this one. Thanks for watching.